Hi, welcome back to our class again. This is Mrs. Teresita B. Moreno. Welcome to Physical Science. And for today, we'll be discussing about the general types of intermolecular forces. So this will be our objectives for today. First, we have to identify the types of intermolecular forces present in among substances, and describe the types of intermolecular forces present in substances. Okay, so for today, since we have already identified how to write down Lewis dot structure, okay, maybe for this time, you will be showing the direction of dipole moment for each molecule. What would be the shape, and what would be the polarity of the given compounds. So for this activity, you will be having a 5-minute time, and then later we'll check your work. So in writing down the Lewis dot structure, you should know how to write the electron configuration of this element. So last 1 minute and 35 seconds. Okay, 10 seconds left. Okay, so let's check your work. Now for number 1, uh, the Lewis dot structure looks like this. So you have fluorine, fluorine, and chlorine. So the central atom is carbon. Then the shape is tetrahedral. Okay, what would be the polarity? So that is polar. What about for number 2? Okay, nitrogen gas. Okay, it looks like that. And the shape is linear. Then it is non-polar. Okay, next, number 3. The Lewis dot structure is, you have there 4 hydrogen and 1 carbon as the central atom. It is also a tetrahedral, non-polar. For water, it is bent and non-polar. So for carbon monoxide, okay, that is a triple bond. That's linear and it's polar. So I hope you got the correct answers. Okay, let's proceed. Now, what are intermolecular forces of attraction, or we call that as IMFA? So these are the 5 intermolecular forces that we are talking about: the ion dipole, the hydrogen bonding, dipole-dipole forces, dipole induces dipole, in London dispersion forces. Okay, let's talk about the first one, the ion dipole forces. Okay, this force of attraction occurs between ion and a polar molecule. When I say ion, we are talking about with charged particles or charged ions and molecules. So for example, we have salt and water. So remember, salt and water are they polar or non-polar? Yes, they are polar, and as you can see, salt has 2 elements found in that compound, or that compound composed of sodium and chlorine. So that's why you have NaCl. And water, you have hydrogen and oxygen. Now this is how ion dipole forces occurs. Now as you can see at the center, for salt, as I have mentioned, it is sodium chloride. Okay, sodium is at the center, and you have there the chlorine, which are the negatively charged. While in the other example, it is salt water, diba? Salt water contains water which has hydrogen and oxygen, and the salt which contains sodium and chlorine. So sodium is a positively charged, while chlorine is a negatively charged. Now what's around it are the molecules of water. So as you can see, the red one indicates the hydrogen, and the white one indicates the presence of oxygen. Okay, this is the ion dipole interaction, okay, such as salt dissolved in water. Now you have here the cation, which indicates the sodium, and the anions, which indicates the presence of chlorine. So in this example, it is ion dipole interaction because the 2 molecules are polar in nature. Okay, the second type is dipole-dipole forces. Okay, when I say dipole-dipole forces, this is a type of interaction where the opposite charges ends of polar molecules. So the strength of the dipole-dipole force is dependent on the polarity of molecules. So it is very important that you know the polarity of the given compounds or that type of molecules, because it would tell whether it is dipole-dipole interaction. Okay, just like in this example, you have hydrochloric acid, since you have hydrogen and chlorine. So hydrogen is a positively charged, while chlorine is a negatively charged. So therefore, there is an attraction. Why there is an attraction? Unlike charges attract, while like charges repel. So therefore, since they are positively and negatively charged, okay, definitely there will be an attraction. In the given example above, okay, these are example of molecular dipole. You have there the water, and the second example, you have molecular dipole again. For the carbon tetrafluoride, you have no molecular dipole, and for carbon dioxide, no molecular dipole. Okay. Alright, so the strengths of intermolecular forces are generally weaker than either ionic or covalent bands. So when you talk about ionic, this is a combination of compound which has metal and non-metal, while covalent is a combination of a compound which has non-metal and non-metal. So in our given example, we have here hydrochloric acid. So hydrochloric acid is a covalent bond or a covalent compound. So as you notice that hydrogen and chlorine has a very strong bond. So hindi siya basta-basta ma-break down. Unlike the intermolecular attraction, which is weaker. Why weaker? Because of the following reasons. Okay. So hydrogen is a positively charged, chlorine is negatively charged, and then this is 16 kilojoules per mole is needed in order to separate the molecules. Okay, in order to separate the two hydrochloric acid. But for the case of hydrogen and chlorine, in order to separate them, you need a greater amount of energy in order for the covalent bond to be separated. Can you guess how much kilojoules does it need, or how much energy is needed in order to break down the bond of hydrogen and chlorine? Okay, so you need 431 kilojoules per mole in order to break the bond. Okay, that's why covalent bond is stronger compared to the intermolecular forces of attraction, which is weaker. Because in order to separate the two intermolecular forces, you only need 16 kilojoules. While when you separate the covalent bond of hydrochloric acid, you need 431 kilojoules per mole in order to break the bond. Another example is the dipole-dipole forces of attraction, which contains the polar molecules of silicon dioxide. Okay, why there are dipole-dipole force? Because there is an attraction between the positively charged and the negatively charged. Now, if these two bonds, two forces of attraction of silicon dioxide in another silicon dioxide, what would be the effect of this attraction have on the boiling point? Like for example in water and oil. Why the boiling point of water is different from the boiling point of oil? So you were able to explain that in your previous assignment, in your research. Why the boiling point of oil or the corn oil is greater than the boiling point of water. Okay, the third one is induced dipole attraction. Okay, when you talk about induced dipole attraction, okay, it involves nonpolar molecule by the surrounding dipole containing molecules. Okay, just like the dipole-dipole forces, it depends on the presence of the polar molecules. So the other molecules needs to be a polar one, while the partial charges in the dipole cause the polarization or the distortion of the electron distribution in the other molecules. Thus, it gives the partial region of a positively charged and a negatively charged in the poles, for example. Now you have here the example. So as the given example, you have there the isolated oxygen molecule, which is a nonpolar. And letter B, you have the induced dipole oxygen molecule. So the other molecule that becomes an induced dipole, it will be attracted to the original polar molecules, resulting to dipole-induced dipole attraction, okay, which leads to the permanent dipole water molecules. Now, the fourth one is the hydrogen bonding. For hydrogen bonding, in this case, very strong dipole interaction is being observed, especially if it involves or it bonds with hydrogen with fluorine, hydrogen with oxygen, hydrogen with nitrogen. So they have very strong dipole-dipole interaction. Now, for example, you have there the hydrogen and fluorine. Hydrogen and fluorine has a very strong covalent bond, while the intermolecular attraction of hydrogen fluoride is very weak. So this, why? Because the hydrogen is present in this bond. So later I'll be showing you a diagram or the flow chart, how you can easily identify what type of intermolecular forces is being shown or exhibited in the given compounds. Okay. Why we say that hydrogen bonding is a weak to moderate attractive force that exists between hydrogen atom covalently bonded to a very small to a very highly electronegative atom, and a lone pair of electrons in another small electronegative atom of fluorine, oxygen, or nitrogen. Now here is a periodic table showing the electronegativity. Let's take a look with oxygen, nitrogen, and fluorine. So their electronegativity ranges from 3 to 4 and less than 1.5. So in your periodic table, you can also easily observe or easily observe the electronegativity of the given compounds. So I hope you have periodic tables already, because you will be needing that, especially in identifying whether the given compound is a polar or non-polar, because it has something to do with the intermolecular forces of attraction among molecules. So here is another diagram showing the electronegativity. It increases from left to right. So ibig sabihin, within the period, it is increasing. So as you go or as you move to the period, the electronegativity increases. But as you go from top to bottom, that is within the group, electronegativity is decreasing. You have also there the metals, the metalloids, and the non-metals as indicators. Okay, the last one is the London dispersion forces. Okay, this is an attraction due to the constant motion of electrons And sometimes it causes temporary concentration of the charge either on one side of the molecules or atoms. Or sometimes it also exists between all molecules. Now, it is named after a German physicist in Fritz, which name as Fritz London. Or we call this one as van der Waals forces, or VDW diagram. So it indicates there the simple atom, which has a negative charge, and the positively charged nucleus. Sometimes London dispersion forces is also considered as instantaneous dipole moment, as also referred to van der Waals forces. In this given example, you have there helium, you have an electrostatic attraction between two helium atoms. So you have there the electrons surrounds helium atom, and that contains the attraction. So it says here that electrons are shifted to overload one side of an atom or molecule. Now, as you can see in the diagram, they only located to a particular side of the molecule. To fully understand the intermolecular forces, let's watch this short video clips, a 10-minute video clips that would explain extensively the intermolecular forces of attraction.
Professor Dave here. Let's talk about intermolecular forces.
He knows a lot about the science stuff, Professor Dave explains.
What is happening when a liquid boils? Why do different liquids boil at different temperatures? To answer these questions, we have to learn about intermolecular forces. These are the electrostatic interactions between molecules. So atoms within a molecule make covalent and ionic bonds with each other, but molecules also participate in interactions with other molecules. Let's look at the different types. First, we have ion-ion interactions. Large ionic solids are held together by these networks of ionic bonds, which are the strongest intermolecular force because they involve formal charges. After that, we have ion-dipole interactions. So first, we must understand what a dipole is. The covalent bonds in a water molecule are polar because oxygen is more electronegative than hydrogen and will pull the electrons in the bond towards itself. Because of the bent shape of the molecule, when we combine these vectors, we see water has an overall dipole, or a side of the molecule with some electron excess and a side with electron deficiency. Dipoles can make electrostatic interactions because the partially negative side is attracted to positive charges and the partially positive side is attracted to negative charges. So when sodium chloride dissolves in water, the sodium ions make ion-dipole interactions with the negative side of water's dipole, and the chloride ions make ion-dipole interactions with the positive side of water's dipole. Each ion can make several of these interactions, which store a lot of energy, which is why sodium chloride will dissociate in water in the first place. Next, we have dipole-dipole interactions. As you can guess, this is when dipoles interact with each other, as with pure water. When in liquid form, water molecules will move in such a way so as to always be making electrostatic interactions between the negative end of one dipole and the positive end of another dipole. In this case, these dipole-dipole interactions qualify for a special title, hydrogen bonds. This is when dipoles generated by NH, OH, or FH bonds, interact with each other. These are just especially strong dipole-dipole interactions. They are especially strong because these are the most electronegative elements, so they will create the most strongly polarized bonds, resulting in a very strong dipole and therefore very strong dipole-dipole interactions. We can almost think of partial charges as some fraction of a formal charge. So the greater the partial charge, the stronger the interaction, though never quite as strong as interactions between formally charged particles. Lastly, we have the van der Waals, or the London dispersion force. These names refer to the same force and are completely interchangeable, so I will arbitrarily refer to them as van der Waals forces. This is the consolation prize of the intermolecular forces because any substance can do it. Only ions make ion-ion interactions, and only covalent molecules with a dipole can make dipole-dipole interactions, but absolutely anything can do van der Waals. For example, take a look at helium. Helium is a noble gas, and due to a full valence shell, it does not make bonds with other atoms. So a sample of helium is just a bunch of helium atoms. Well, the electron cloud around a helium atom will at any time be slightly lopsided, or skewed towards one direction. This will result in something called a momentary dipole. This means one side of the atom is ever so slightly partially negative, and the other side is slightly partially positive. This is much weaker than a formal dipole, but it still exists and can be measured. If a momentary dipole approaches another atom, it can generate an induced dipole, meaning the slight partial negativity repels this electron density over to the other side of the atom, so it will also have a slight dipole. And then there can be a momentary dipole-induced dipole interaction, that is the van der Waals force. This is a weak and fleeting attraction, but this is all that monoatomic species and non-polar covalent compounds can do. And for very large molecules like some hydrocarbons, the force can become significant. So the ion-ion force is strongest because it involves interactions between formally charged particles. Ion dipole is next because it involves a formal charge and a partial charge. Then dipole-dipole, which is between partial charges, and van der Waals, which is between tiny induced dipoles. To see how intermolecular forces dictate phase change, let's do a thought experiment. First, recall that a solid's particles are rigidly packed and not moving. A liquid's particles are moving, but they are still close together and interacting. Gaseous particles are moving and they are far away from each other, so compared to liquids, they basically don't interact. So let's pretend we have three substances: helium, water, and sodium chloride. We will place them at 0 Kelvin, or absolute zero, which is the lowest temperature possible, a complete absence of heat energy, where there is no energy available for motion. Here, everything, even helium, is a solid. In order to go from the solid to the liquid to the gas phase, heat energy has to go into the sample and overwhelm the intermolecular forces that are occurring. In a liquid, there is some energy stored in electrostatic interactions, and whatever amount that is precisely the amount of heat energy that has to be provided to liberate the molecules into the gas phase where they are not interacting and not storing energy, because nature will not tend to go to a higher energy spontaneously. So the energy stored in these interactions has to be provided in some other way. This means that the stronger the forces between the molecules, the more heat energy we will have to provide to melt and boil the sample. So let's take our three substances, slowly raise the temperature, and see what happens. Helium, as it is only participating in incredibly weak van der Waals forces, needs only a minuscule amount of heat energy to disrupt these weak interactions. That's why helium will melt and boil at barely 1 degree above absolute zero. Water, on the other hand, is participating in strong dipole-dipole interactions called hydrogen bonds. There is a significant amount of energy stored in these interactions, so we will need considerable heat energy to overcome them. Water melts and boils at 273 and 373 Kelvin respectively. Lastly, sodium chloride is making extremely strong ion-ion interactions, so it will take a huge amount of energy to melt and boil this solid. It melts at 1074 Kelvin, which means there's a lot of energy stored in the ion-ion forces. We can use this information to decide which of a given set of compounds might have the highest boiling point. When we ask this question, we are really asking which compound is generating the strongest intermolecular forces. The stronger they are, the more heat energy we will need to pull the molecules apart and put them in the gas phase, so they will boil at higher temperatures. We need to be able to look at a molecule and decide what kind of interactions it will make. If it is a covalent compound with non-polar bonds, it can only do van der Waals. If it is a covalent compound with polar bonds, then we must look at the geometry to see if there is an overall dipole. For example, water has a dipole, but carbon dioxide does not, because even though carbon-oxygen bonds are polar, the direction of these polar bonds causes them to cancel each other out, and the molecule is non-polar overall. Similarly, compare BF3 with NH3. Again, the molecular geometry determines that this is non-polar, because the vectors precisely cancel each other out. But with ammonia, all the bonds point somewhat towards one direction, so ammonia has a dipole. CF4 is nonpolar, again because of geometry, but CH3F has just one polar bond, so that has a dipole. If a molecule has a dipole, it can do dipole-dipole interactions. And lastly, formally charged ions participate in ion-ion interactions. See which compounds can do what, and you will be in business. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Now, after watching the video clips, it is clearly explained there how the different intermolecular forces of attraction happens. So, to sum up with the intermolecular forces of attraction, okay, let's proceed to the next slide. Okay, this is a diagram that will show or will help you identify whether the given set of molecules is dipole force or London forces, hydrogen bonding or ion dipole forces, or is it ionic bonding. Now all you have to do is identify whether there is ions involved. If yes, then ask again, are polar molecules and ions both are present? If yes, then it is ion dipole force. If no, then it is ionic bonding. Just like, for example, sodium chloride, nitrate, and ammonia. Now, going back to the other side, are ions involved? If your answer is no. Are polar molecules involved? If yes, are hydrogen atoms bonded to nitrogen, oxygen, or fluorine atoms? If your answer is yes, then it is hydrogen bonding. If no, then it is dipole-dipole force. Now, going back to the question, are polar molecules involved? If no, then London forces of attraction, induced dipole may be present. So that is how you are going to identify what type of intermolecular forces of attraction is present by asking these following questions or remembering these following questions. Now let's proceed to our activity. Okay, in this activity, you will be identifying what type of intermolecular forces present among the following given. Letter A, you have the sulfur dioxide. Then letter B, you have sodium ion and formaldehyde. Okay, number 3, or letter C, 2 carbon dioxide. And letter D, you have ammonia and water. Then iron and oxygen gas. So I'll be giving you 5 minutes. Okay, last 1 minute and 39 seconds. Okay, last 53 seconds. Okay, time's up. So we'll check your work. Okay, let's have number 1. Okay. So two sulfur dioxide molecules. So our answer will be London dispersion and dipole-dipole. Okay, letter B. Okay, sodium ion and formaldehyde. So what do you think will be our answer? Okay, very good. So you have the London dispersion. Okay, let's have letter C first. Okay, before going to letter B. Okay. So for letter B, we have sodium dispersion ion dipole. Okay, since you have there, sodium is positive ions, and you have there formaldehyde is in London dispersion. Then letter D, you have London dispersion, dipole-dipole, and hydrogen bonding. So in short, in one compound, it might be having two or more type of intermolecular forces of attraction. And then letter E, you have London dispersion and ion-induced dipole. Now, what about for this activity? So you will just complete the statement given. So you have 1 minute for number 1. The attraction happens between polar molecules. The charges align so that the blank pole of one molecule is attracted to the blank end of the other molecule. So this kind is called blank interaction. Look at the arrow. Okay, so let's check your answer. Okay, let's have. Okay, the first is partially negative, and then you have positive, and the interaction is dipole-dipole. Okay, let's proceed to number. Okay, let's have number 2. The blank sodium ion is attracted to the partially blank end of water molecules. This attraction is referred to as blank. So let's check your answers. So the first blank is positive, and then since sodium is a positive ion, okay, partially negative towards the end of water, and it is ion dipole attraction. Okay, number 3. Okay, number 3 is a blank ion or blank approaches a neutral nonpolar substance. This results to a distortion of the substance and leads to the development of positive and negative poles. This attraction is called blank. Look at the diagram. Okay, what do we call the positively charged? Okay, so let's check. So you have a positive ion, or we call that one as cation. And then the attraction is called as ion-induced dipole. As you can see in the given diagram, there is an induce. Okay, number 4. Okay, a permanent blank approaches a neutral nonpolar substance, resulting to a blank dipole. This form of attraction is considered as blank. So let's check. Okay, the first blank is a dipole approaches a neutral nonpolar substance, resulting to a temporary dipole, and this attraction is considered as dipole-induced dipole. Okay, last. So last is number 5. The partially blank oxygen of one water molecule is blank to the partially blank hydrogen of the other water molecule. This is called as or a blank. Okay, so let's check. So the first blank is negative because the oxygen is negatively charged. Then it is attracted to the partially positive hydrogen of the other water molecule. This is called as hydrogen bonding. Okay, for this activity, you have 3 minutes. You'll be identifying or the description of intermolecular forces. So you have column A with column B. So column A are the statements and column B are the choices. So you have 3 minutes to work on this. Just write down the letters of the correct answers. So let's check. So let's have number 1 is letter E, that is dipole-dipole. Number 2 is letter G, ion dipole. Number 3 is letter A, hydration. Letter J, number 4, which is dispersion forces. Okay, number 5 is letter B, ion-induced dipole. Okay, letter C for number 6, H bonding or hydrogen bonding. F for number 7, dipole-induced dipole. Number 8 is letter D, polarizability. And number 9 is letter H, that is dipole. And number 10 is letter I, cations. I hope you learned something from today's discussion. Okay, I hope you learned something from today's discussion. Once again, this is our references, the physical science, and some of the links that is posted in the as we go with the presentation while ago, and we are using this modules, page 109, 132. Please do visit your Google Classroom. The activity for the week is already posted, and for the quiz, it will be posted on Wednesday. So that you have still time to work with with activity first. That is more on the applications of the intermolecular forces of attraction. So that is a research activity. And as I have mentioned, when you have research activity, please do include the website or the source of informations, the sites, or the links where you got all those informations. So have a blessed day, good luck, and keep safe, everyone.